right? So if I have an equation solved for y in terms of x, or x in terms of y, or one variable in terms solely of the other variable, then it's an explicit form of a function. If it's not, then it's not. All right, so then that becomes the implicit form of the function, if it wants to cooperate. Okay, so the implicit form is a little bit more functional because it allows you to take an equation in any form and find its derivative. All right, so it doesn't have to be in any particular form. You can still find the derivative of that function. All right, so there's a procedure, but I'll walk you through the procedure. It's pretty straightforward. There's a little bit of a twist along the way here that's somewhat inconsistent with the way that we've been doing it, or at least seemingly inconsistent. It'll turn out that we had been doing it this way all along, but I figured I'd show you the how first, and then we'll talk about the why. All right, so it asks us to graph this. That's easy enough because that's just a circle. A circle with the center at the origin and a radius of 4. So I'm going to go out 4 units in each direction and draw a circle. And kinda. All right, now how do I edit it? Edit. Okay, I clearly don't know how to use this function. I mean, it produced a circle, so I'll take that as a win. I don't know how to adjust the fill. All right, well, I needed a circle, I got a circle. Just not quite what I had in mind. All right. Anyways, I need to take the derivative of this implicitly, which, the directions explicitly state something that is implied, which is kind of weird. But it's basically telling us don't solve this for y and then take the derivative, work with it as is. All right, so this is how we take a derivative using implicit differentiation. Let me do a little zooming here. I'm going to rewrite the function. All right, we're going to take the derivative of any term involving an x the way we always did. All right, so power rule, product rule, quotient rule, whatever. No change there. When it comes to taking the derivative of a term that has a y in it, though, a slight adjustment needs to be made. So the first part of it would be to take the derivative of it the way you would if it were an x. So apply the power rule. 2y to the first, right? So just a 2y. But for any y derivative, we're always going to multiply by dy dx. All right. So always when you're taking the derivative of a y term, you're going to multiply by a dy dx. All right, so if this were x squared, it would just be a 2x. But because it's a y, it gets a dy dx multiplied at the end. All right. That's the big adjustment. All right, and we'll get into why that is the case in a little while. But for now, it's just a skill. Derivative of a constant, doesn't matter what method you're using. Definition of a constant is that there is no change. A derivative is a rate of change. So constants always have derivatives equal to 0. All right. So take the derivative. You can read through the steps if you want, but it's all basically going to say the same thing. just more explicitly. It's going to say, find the derivative of everything the way you always did. Just anytime you take the derivative involving a y, slap on a dy dx. All right. And once you do all that, we want to solve for dy dx. All right. So I'm going to subtract off the 2x. So I'll have 2y times dy dx equals negative 2x. And then I'll divide both sides by a 2y. And that'll give me dy dx equals negative x over y. And so that would be our derivative. Now, if you want to, I mean, I'm not going to make you do it, I don't think anyway. Maybe I will, I don't know, I don't remember. But you could solve this for y in terms of x, then take the derivative, and you get something that looks incredibly different, but they both represent the same thing, right? So this method is, it's new, so when you're dealing with something that's new, it's not always something you want to, gravitate towards initially, but then once you realize that this new technique is actually a simpler technique, a better technique, then you start to really appreciate it, right? So, I mean, the derivative of this is a disaster if you solve for y first, right? It's, let me see if I figure it out. I think it's 1/2 times 16 minus x squared to negative 1/2 times negative 2x, so that would be negative x over the square root of 16 minus x squared, I think. I don't know, you could try it. I mean, I think that's enough for you to say that you don't want to do it that way. So that's negative x over y, that seems much nicer, right? Part B is asking for all the points where the graph has a horizontal tangent, right? Horizontal tangent, you can get that visually, or you can get it off of the derivative equation. Visually, we're looking at, that's not good. Undo. I'm going to use the line draw tool feature. That's one of them. The only way that I would be able to draw a line that is tangent to a curve, but that line is also horizontal, would be if that tangent line touches at a turning point. All right, and we have 2 turning points. All right, so each of these would be a tangent line, a horizontal tangent line. I'll just denote that with an HT. All right, that happens when x is equal to 0, in both cases. There's also some y values associated with that too. You could say the y values are 4 and negative 4, but generally we focus on the x values. All right, if I'm looking at a vertical tangent, looking at something like this, not like that. Really gotta hit this thing every single time, that stinks. All right, there you could identify the x values also. Those are happening at 4 and negative 4. So you can get it off of the picture, provided you can construct the picture. If you have trouble making the picture, I mean, you can look ahead in the package. You see some pretty crazy looking functions. So it's not always going to be something that you can draw a picture for. If it's an equation that's defined in terms of x and y, how are you going to put that in your calculator? Not easily. Right? So analytically, to the algebra method, find all points where the graph has a horizontal tangent. Well, a horizontal tangent happens when the derivative is equal to 0. All right, so I'm going to take my derivative, which is negative x over y, and set it equal to 0. Cross multiply, and I get x equals 0. So at the x values of 0, I have horizontal tangents. Now I could also figure out the y values that go along with that, because x squared plus y squared is equal to, what was it, 16? So that's the same as saying y squared equals 16, making y equal to plus or minus 4. So if I actually wanted coordinates, I could state the coordinates. Generally, again, we're just looking for the x values, but I have a pretty good avenue here to come up with actual coordinates, and the computation isn't that bad. All right, so we have horizontal tangents at 0, comma, plus or minus 4, two unique coordinates. All right, now our vertical tangent. Vertical tangent happens when the derivative is undefined. So I'm just going to take my derivative and set it equal to 1 over 0. So negative, what was it, negative x over y or negative y over x? Oh, negative x over y. Okay. Set that equal to 1 over 0 and solve. When you do that, you get y equals 0. Go back to your original equation and solve. You get x squared equals 16, making x equal to plus or minus 4. So if I needed coordinates, I can now confidently state that my vertical tangents would be at plus or minus 4, comma 0. But again, you can get that just by looking at the picture in this particular case. But if you had to do it analytically, it's still not terrible. All right. So I'm not going to, I don't think I am. No, definitely not. I'm not going to make you do it the other way just because it doesn't really serve a purpose. I think you believe me when I say the other way is a pain and you don't want to do it the other way. That's why we're learning this way. All right. So as long as you can continue to believe me when I say stuff like that, I won't make you do it the other way. So it's the longer way. All right. Choosing to use implicit differentiation because it makes life easier. All right. So find the first derivative. You see that it's asking for the first derivative, so you know at some point the second derivative is going to come into play. All right. So we have two components here separated by a sum. Those two components themselves are products. So that's going to involve the product rule. All right. So we're looking at x squared y plus y squared x, and then equals to negative 2. So from just looking at the x squared y, we have two factors. So I have to use the product rule. All right, so my first function multiplied by the derivative of the second. All right, so x squared multiplied by the derivative of y. All right, so again, anytime we take the derivative involving a y term, we're going to take the derivative as if it were an x. We'll do it the way we would always do it, but then we also are going to multiply by dy dx. So the derivative of y would normally be a 1, but because it's a y, we're multiplying by dy dx. All right, so you're basically asking yourself, okay, if that y was an x, what would its derivative be? All right, 1, okay, but it is a y, so I have to multiply by dy dx. Plus my second function, y, times the derivative of the first, which is just 2x. All right, so product rule, except, again, when we go to take the derivative of the y term, we have to slap on a dy dx. All right, now for the second part, also a product, so we'll use the product rule. First function multiplied by the derivative of the second. Easy enough, because the first function, y squared, would be then multiplied by the derivative of the second, which is just a 1. Plus the second function multiplied by the derivative of the first. First function multiplied by the derivative of the second. What's the derivative of that?
Mr. How come we don't put dy or dx after the purple y?
Because we didn't actually take its derivative. All right. So first function multiplied by the derivative of the second, now plus the second function multiplied by the derivative of the first. So what's the derivative of y squared? 2y times dy dx. And the right-hand side? 0, because the derivative of a constant is always equal to 0. All right, so this is a mess, but we've actually successfully taken the derivative. We did the hard part, now the rest is algebra. All right, so it's probably a good idea to clean it up a little bit, just put it in a nicer form. So I'm going to multiply these. That's just going to become x squared dy dx. And multiply these, so plus 2xy. Plus y squared. Plus 2xy dy dx. And the whole thing will be equal to 0. Alright, so the big question would be, alright, now what? Well, my goal is to find the first derivative. The first derivative is dy dx. So I want dy dx equals. Right? So it sounds like I need to isolate my dy dx stuff. Right? So I'm basically going to take anything that doesn't have a dy dx attached to it and send it over to the other side. So x squared dy dx plus 2xy dy dx equals, you do it in either order already, there's negative 2xy minus y squared. Alright, so a little bit better. What can I do on the left hand side? What should be my next move? Factor out a dy dx. Because that's the thing that we want to get alone, right? So if we factor that out, we can isolate it. And then we could divide out the x squared plus 2xy. That's pretty beefy. That's the easy way to do it. I mean, I don't know how much people like to torture themselves, but if you actually wanted to see, see but not do, if you wanted to see the other way, you could, I posted a video for my AP class this morning. So you could just take a quick look. I mean, you don't even have to watch the video. Just kind of scroll along and just look at the completed solution, and you'll get a sense. All right, this is definitely the way to go. All right, but you can see how it calls upon knowledge of all the stuff that we've been covering. There's product rule, there's power rule. The only thing in here I guess we don't really have too much of is chain rule. Although it is there, it's just it doesn't seem like it's there. That's the underlying concept that I said we would talk about. But it's kind of in there, just it doesn't seem like it's there. I guess quotient rule's not there. But yeah, if you don't know your product rule, if you don't know basic derivative rules, then you're out of luck when it comes to stuff like this. All right. Now it's asking us in the second question to find f prime of 2. All right. So that's actually, the way it's written is sort of a typo. It should, so I'll take this if somebody wants to submit it. is because it's not a function of x. It really should be the derivative when x is equal to 2. All right, so the derivative of y with respect to x when x is equal to 2. All right. So we have a couple of things that we have to do here, because my derivative is not only in terms of x, but it's also in terms of y. So I need to know the y that goes along with that x. So I'll start with that. All right, so I'm just replacing in my original equation all of the x's with the 2, and then I'll solve that for y. All right, so we're looking at 2y squared plus 4y plus 2 equals 0. And then we have a common 2 that could be factored out. Which makes this a perfect square trinomial. What are my factors? Y plus 1, y plus 1, which means that y would have to be equal to -1. All right, so at long last, we have the y value that goes along with the x value of 2. So now we have everything we need in order to plug in to my derivative. All right, so dy dx, which again was a pretty funky looking thing. It had x's and y's. Everywhere I have an x, I replace it with a 2. Everywhere I have a y, I can replace it with a -1. All right, so I need -2xy minus y squared. Maybe a little too big. -2xy minus y squared. Oh, I don't need the y. So again, the x value is 2. The y value is -1. Then on the bottom, x squared plus 2xy.
So I'm just putting it into dy dx
From part A, exactly. And this is one of those kind of problems where you do all this work to find out that it's just undefined. And you're like, wow, that sucks. I mean, maybe it doesn't suck, I don't know. But I'd like to get a numerical answer related to that. But then it begs the question, well, okay, what does undefined mean in this context? Well, it could mean a vertical tangent like on the previous page, right? So we would have 0 in the bottom of a fraction. That's giving us an undefined slope. Undefined slope could be a vertical tangent. The problem with that, or at least on this level, is, well, I don't know what this graph looks like to begin with. So I can't verify whether or not it's a vertical tangent or some kind of discontinuity. Right, because I couldn't get it solved for y in terms of x, and then on top of that, I couldn't look at the picture. Right, so I mean, there are ways to do it. It's just a little bit beyond what we need to do for this course. Right, so at this point, we would just say answer undefined. All right, and then number 3, asks us to graph the hyperbola. We'll come back to the graph part, because in order to come up with the equation of a tangent line, what we need is the point and the slope. We have everything we need without even looking at the graph in order to come up with the equation of the tangent line. And this is a pretty good problem, because it relates to a solid misconception, common misconception that folks have when it comes to derivatives. And that is, I mean, it's probably more commonplace than it should be, because I think it should be common sense. The common sense part of it should be that just because an equation is presented to you in a particular form doesn't mean you have to leave it in that form. All right, so I look at this and I say, oh, look, a quotient. Then I would say, well, I don't like the quotient rule, so I'm going to change this so that I don't have to work with the quotient rule. Many of us are good at doing stuff like that. Sometimes we're good at changing it out of being a quotient rule problem into another type of problem, but then we're not good at taking the derivative in that other form. That's kind of a problem, but that's something that you can work towards correcting. All right? But there are enough folks that don't even know that changing the form of an equation is even an option. All right? So we need to get kind of through to those individuals, because that is so important. Because I look at this, I say quotient rule. Yeah, sure, you can do a quotient rule. But what happens when I take, you know, we got the low D high, that part's all right, but what happens when I do the high D low? What do I get? What's the D low gonna be? Zero. So a big chunk of my quotient rule is gonna zero out. If that ever happens, then that's telling us that we didn't need to use quotient rule to begin with. Because I could rewrite this as 1/4 x squared minus 1/9 y squared equals 1. And instead of burdening myself by using the quotient rule, I can do what instead? Power rule. Simple power rule. So 2/4 x to the first power, so really 1/2 x minus 2/9 y to the first power, but it's a y that we're taking the derivative of, so I'm going to multiply by what? dy dx. All right, and again, we don't know why we're doing this yet. We just know that we have to do it. It's not an x, so we're slapping on a dy dx. There's a really good reason for it. It's just, it's better understood once you have a sense of how to do it. All right, so you will have that question answered, if that happens to be a question. I don't know. Some people don't even care. Like, this will give me the answer? Cool, good enough. And if that's the case, that's fine too. All right, so I'm going to solve for dy dx. So I have negative 2 over 9 y dy dx. I'm subtracting the 1/2 x to the other side, so negative 1/2 x. Then I'm going to divide by negative 2/9 y. And I get dy dx equals, what, 9/2? No, just 9, right? When you keep 9/4. When you keep change flip, the negatives are going to go away, but you don't need to keep change flip for that. But 1/2 will be multiplied by 9/2, so 9/4. So 9x over 4y. All right. Now we want this specifically at the point 2, 0. So I want dy dx specifically at the point 2, 0. So 2 goes in for x, 0 goes in for y. Undefined. All right, so that's where the graph comes into play, because I'm looking at this and saying, well, the possibilities are the derivative doesn't exist because maybe there's no graph there, or it's a vertical tangent. In order to understand that, you need to have a sense of what the hyperbola looks like. Now, there's two ways to go about doing this. One way involves you knowing a little something from pre-calc. The other way involves you knowing a little something about your graphing calculator. All right. So for this particular problem, I'm actually going to solve for y in terms of x. All right. So I'm going to subtract off the x squared over 4. We'll have negative y squared over 9 equals 1 minus x squared over 4. Then I'll multiply through the 9. Well, actually a negative 9. And we would have y squared equals negative 9 plus 9x squared over 4. And then I need the root. And you don't have to worry about cleaning it up because the calculator is going to understand it just fine. The big twist here is just remembering that you have to have a plus or minus. All right, so our equation has a plus or minus, but our calculator doesn't have a plus or minus button. Okay, so I'm not going to look at the derivative. I'm just going to look at the original function. Because I think it's going to be easy enough to eyeball where 2 comma 0 is on the graph. All right, so I'm going to put in the square root of this. So the square root of negative 9 plus, and then the fraction 9x squared over 4. So that's only the positive variation. Right? So we have plus or minus. We need the negative version of that. So I can retype the whole thing just with a negative sign in front of it. I don't want to do that. Instead, what I want to do is tell the calculator for my y2, I just want the opposite of y1. Alpha trace y1. All right, so that's what I meant before about knowing a little something about your calculator, because if you know that that's something that you can do, it simplifies things. Because if you have a really complicated y1, just negating it, that shouldn't be too difficult. All right, unless you don't know about this technique. All right, so zoom 6. That's the top half, that's the bottom half. Calculator kind of lets us down a little bit when it comes to hyperbolas and ellipses and circles, any form of conic section. It makes it seem like they're not connected, but they actually are connected. So you have to assume that there's a solid, smooth curve going through those points. All right. So what I just need is a rough sketch of that. Yeah, so something like that. Yeah. I forget what classes I talk about certain things in. Have I ever gone over like the whole bathroom thing in this class?
Right when you walked out, yeah.
Oh,
Last
okay.
time, yeah.
Last time? Oh, okay.
Yeah.
Could somebody just tell him? Because he asks every time.
I think he's the only one who still asks.
Is that, so I must have missed it. He must not have been in the room. Yeah. Yeah. I mean, I guess if it was like a freshman study hall or something, I'd want them to ask. Just go. So this is roughly what the graph would look like. I mean, that's a better representation. This is garbage by comparison. But it gets the job done because what we're doing is we're looking at 2, 0. And we got an undefined slope, right? So the undefined slope could mean, again, a couple of different things. Maybe it means that there's a discontinuity, all right, or a cusp, or a corner in the graph. but it could also mean that there's a vertical tangent. In this case, it does look like we're dealing with something that goes vertical. So if I had to put a tangent line on this, such that it goes through this particular point, it's probably going to look like this, or something along those lines. Let me use the line draw tool. Close enough. All right, so that's what my tangent line would look like. Now, this question is asking us to write the equation, find the equation of the tangent line to the graph. All right, so the equation of the tangent line is a vertical line. I don't need a point slope form or anything complicated. It's just a line x equals 2. The vertical line x equals 2. All right, so we did have to do a little bit related to the graph to just kind of flesh out what the circumstances were that led to the undefined slope. Because again, it could have been any of those other possibilities. By looking at the picture, we're able to determine what it is. That's why the previous question didn't say something like find the equation of the tangent line, because in that one you couldn't look at the picture. So I wouldn't ask you to. I wouldn't ask you to find the equation of a tangent line for something that you couldn't actually visually make a determination on. Now that one, when you plug in, you know, it doesn't matter what the coordinate is, but if you plug in a coordinate for x and y, you get a real number, then it's fair game. You know, you have a slope, you have a coordinate, you could write the equation of the tangent line. But when it's undefined, for something like this, you would not know. But for this, you can actually verify. All right. All right.